Have you ever walked by a gorgeous building in New York and wonder how people afford it? Real-est is here to help you find out. We will teach you how to use linear algebra to estimate the price of an apartment based on factors like square footage, number of bedrooms, and neighborhood rating. As rent continues to climb across the city, we will explore how mathematics can reveal the underlying patterns of New York's housing market and even help forecast future prices. Every building in New York has its own unique character. The New York City skyline features skyscrapers, brownstones, colonial, Greek revival, and many other architecture styles. In linear algebra, we can define this variety with a span. Together, these differences create the basis of the city's skyline. Let's see how basis and span can help us represent real apartments as vectors and how we can tell if our sample truly captures the diversity of the housing market. A basis is a set of vectors that are linearly independent and span a vector space. That means two things. One, none of the vectors can be written as a combination of the others, and two, together they can describe every possible vector in that space. Now, let's connect this to real estate. Imagine we want to evaluate an apartment using three features. 1, its size in square feet, 2, the number of bedrooms, and 3, a neighborhood rating from 1 to 5. Each apartment can then be represented as a vector in three-dimensional space. For example, we have apartment 1. Here, 1,000 represents the square footage, 2 represents the number of bedrooms, and 3 is the neighborhood rating. If we collect a few apartments like this, we can think of each one as a vector. Now, we want to determine whether these apartments form a basis for R3. In other words, is our sample of apartments a diverse sample, or are they just scaled versions of each other following a stable pricing trend? If they're too similar, for example, if every time the square footage increases, the number of bedrooms and neighborhood rating also increases in the same ratio, then we don't actually gather any new insight from them. In that case, the vectors are linearly dependent. But if each apartment captures a different relationship between the three features, maybe one is large but in a less desirable neighborhood, another one is small but in a prime location, and a third is somewhere in between, then they point in different directions in the space. That means they're linearly independent, and together they span the entire three-dimensional space of possible apartments. If you put them as columns of a matrix, forming matrix A, seen here, and calculate the determinant using this formula, we get determinant of A is negative 1400, which is not equal to 0, so the vectors are linearly independent and form a basis for R3. So, by arranging these vectors into a matrix and checking whether the determinant is 0 or not, we can tell whether our sample truly represents diverse and independent factors in the housing market, or whether they're all just variations of the same predictable pattern. Now, on to the next topic, homomorphisms.
In the city, two buildings might look similar, but their prices can be wildly different. Let's compare how different features translate into value using homomorphisms, a concept from linear algebra that means a map that preserves structure. If I add two vectors or scale them and the transformation preserves that relationship, it's considered a homomorphism. This idea matters because it lets us see how information is transferred between spaces, like how neighborhood features translate into real estate value and factor into pricing decisions. Now let's apply that idea to Central Harlem in the Upper East Side using three real estate features from a 2025 New York City dataset. Each neighborhood becomes a vector in R3, with each variable representing the square footage, livability score, and median income respectively. Onto defining our linear map, H maps a three-dimensional vector space onto another three-dimensional vector space and is defined by multiplying the matrix A containing the different weights that will be assigned to the pricing indicator stored in the vector X. So P1 weights income a bit more, P2 leans hardest on square footage, and P3 gives extra emphasis to livability. After plugging in the numbers, we get the following values. In every case, the Upper East Side score is about 3 to 3.5 times Harlem's, which is very close to the actual gap in price per square foot, roughly $1,000 for Harlem versus $3,650 on the Upper East Side. Among the three, P2, where square footage is weighted the highest, comes the closest to mirroring real-world data, as it most accurately reflects the real 3.65 gap, showing that square footage is often weighted the highest when it comes to real-world pricing decisions. All three indicators come from the same homomorphism, allowing us to analyze different blends of the same data. So instead of random scores, we've built three structured views of Harlem versus the Upper East Side, all backed by real livability, square footage, and income data, and we are able to see which blend aligns best with how the market actually prices these neighborhoods.
Suppose we have 3 apartments and we can record their square footage, neighborhood rating, and price. Here, the first column of A is square footage. The second is neighborhood rating. X represents how much each factor affects the price, and B shows the actual prices. We can write the systems of equations. Now we solve step by step. Take the first 2 equations, multiply the first equation by 5 and the second by 4 so we can eliminate x2. Subtract the first from the second, then plug x1 equals 5 into the first equation. So our solution is x1 equals 5, x2 equals 8. This means each square foot adds $5 to the price, and in the simple example, the neighborhood rating didn't change the price. By solving ax equals b step by step, we can see how linear algebra turns apartment features into a simple model for predicting prices.
With so much mathematics, how are we to keep track of it all? Here's a quick summary to recap all of the linear algebra we just learned and how we used it to predict prices in the housing market. Each apartment can be thought of as a vector, defined by its features, square footage, number of bedrooms, and neighborhood rating. Together, these form a matrix that captures the structure of New York's housing market. When we solve ax equals b, we're finding how much each feature contributes to price, uncovering the hidden weights that shape value across the city. By solving systems of linear equations, we minimize error and build a model that can predict future prices from new data. Linear algebra turns thousands of scattered listings into a clear, predictive system, showing that even in a city as unpredictable as New York, there's a logic beneath the skyline.